Background. Hydrological watersheds are natural subdivisions of the landscape and exercise influence on other natural and man-made features. Wetlands are among the most sensitive of natural features and are vital components of the habitat, requiring protection from adverse impacts that may be caused by human development and infrastructure projects. Indeed, NEPA requires transportation planners to consider possible impacts on the hydrological system, including stream crossings, floodplains, land cover, and wetlands as part of maintaining the ecological and biophysical balance within the local watersheds. Amakudzi and Meyer, 2006. This research describes the use of a collaborative, interactive, and iterative multi-scale approach to assess and rank hydrologically segmented features and wetlands to deliver enhanced understanding of how these biophysical systems are affected by transportation infrastructure projects. This lecture addresses a two-level object-based landscape analysis computed from hydrological subwatersheds from Hydrologic Unit Code 12 level, HUC 12, wetlands, and a subsegment of the proposed Interstate 269, I-269 proposed bypass around Memphis, Tennessee, in the southern United States of America, as major objects of interest. Firstly, parameters are extracted per watershed from percentage of wetlands, zoning, existing and current developments, and density of perennial and intermittent streams. Watersheds are ranked according to the potential for risk on the natural environment, as described below. The watersheds are considered as primary objects in this hierarchical landscape analysis. After ranking these objects, the next step in the hierarchical analysis process is identifying and ranking wetlands based on potential for adverse impact. For each watershed, topographic analysis, computed from LIDAR elevation data, and computer-assisted image interpretations are performed to enhance the delineation of the wetlands. Wetlands are analyzed according their distance from planned developments, planned roads in the I-269 corridor. It should be recognized that there are limitations inherent to geospatial data and their analysis within any research framework, and the practical implementation of innovative contributions for geospatial analysis depends upon properly designing and structuring approaches that may be implemented in a practical and feasible framework available in readily available GIS software. In this paper, a top-down GIS framework for landscape analysis is proposed using hydrological watersheds as reference objects for segmentation of the landscape. This segmentation facilitates the geographical analysis of biophysical subdivisions of the landscape based on a watershed approach to conduct contextual, geometrical, and hierarchical analysis. The overall idea is quite similar to standard approaches in object-oriented landscape analysis. However, the use of watersheds as a segmentation layer enables the analysis to consider biophysical subdivision as parts of transportation corridor planning and enables the use of output results in cumulative cost services that may be employed to refine land use and corridor plans and improve agency coordination during the NEPA process. Landscapes are shaped by the interaction of social and ecological systems, Brunkhorst, 2005. Current and future use of land, productivity and patterns of sustainability are continually modified by humans within the landscape in spatial scales across time in different magnitudes, Ono et al., 2005. For environmentally focused transportation planning, ecoregions and hydrological watersheds are key concepts that must be considered in landscape analysis. Understanding landscape and watershed characteristics, the geographic context of sensitive environmental resources, and the services provided by natural systems, is vital to providing balanced solutions for sustainable development amidst natural resources that face economic and social issues. Despite the similarity in some points of view between creating subdivisions of ecoregions and watersheds, a common misunderstanding of each of these landscape subdivision frameworks has resulted in inconsistency in their use and, ultimately, to ineffective application in addressing landscape analysis. Omernik and Bailey, 1997. Complex spheres of interaction reflecting human values, identity, and activities affecting landscape change, Brunkhorst, 2005. The traditional methods of classifying remote sensing data are based upon statistical and cluster-based classification of single pixels in a digital image, Lillesand and Kiefer, 2004. Recent research indicates that pixel-based classification methods may be less than optimal in producing high-accuracy land use, land cover maps since they do not consider the spatial relationships of landscape features, Shiwi et al., 2001. For example, A significant proportion of the reflectance recorded for a single pixel is derived from the land area immediately surrounding the pixel, Townsend et al., 2000. Analyzing at the polygon object scale enables imagery classification to move beyond this traditional problem. Contemporary object-based landscape analysis uses parameters derived from hierarchy, context and geometry of the image objects rather than pixel values. Despite a successful history with remote sensing, the accuracy of pixel-based image analysis can be compromised when applied to high-resolution images, Nobrega, 2007. The development and practice of object-based classification has grown as have the variety of methods and approaches of incorporating spatial context into the classification process. Most object-based approaches complement the axiom of landscape ecology, that it is preferable to work with a meaningful object representing the true spatial pattern rather than a single pixel, Blaschke et al., 2001. Furthermore, the development or use of objects, at one or multiple scales, is always an initial primary phase of the analysis which emphasizes capturing, extracting, or refining the size, shape, and distribution of features of interest. Object-based classification can be functionally decomposed into two major steps, segmentation and classification. In the segmentation step, relatively homogeneous image objects, polygons, are derived from both spectral and spatial information, Benz et al., 2004. In the classification phase, image objects are labeled as to their class membership by using established classification algorithms, knowledge-based approaches, fuzzy classification membership degrees or a combination of classification methods, Sivko et al., 2002. The commercial software package, Trimble eCognition Developer, formerly Definions Developer, has been well received as a tool for performing object-based classifications of land cover. An example list of scientific papers using eCognition for various land cover mapping tasks is available at http://www.ecognition.com/learn/resource center/show more. Type equals scientific %20 paper. For automated generation of segmentation objects, the application uses a region-growing multi-scale segmentation algorithm for the delineation of image objects. The application also enables pre-existing spatial features to be used as objects within which segmentation may be constrained. eCognition provides two different classification methods that may be used separately or combined, a sample-based nearest neighbor classifier with fuzzy logic capabilities and a classifier that enables the development of hierarchic class membership through a set of rule-based fuzzy logic membership functions. This lecture presents an implementation of constrained segmentation in which naturally occurring objects provide the initial basis for identifying relevant features on the landscape within which classification and analysis that implement geobia theory are explored. No segmentation objects are computed, since the objects of interest, watersheds and wetlands, already exist, and segmentation statistics are generated for these areas and used in subsequent phases of analysis. The method combines intrinsic and extrinsic information extracted from the objects and the analyses are organized hierarchically. Driven by the need to find a balanced solution among conflicting scenarios and because of the vast and growing availability of geospatial data, decision-making theory has been explored by the environmental assessment community, including transportation planners. Multi-criteria decision-making is a systematic methodology to generate, rank, compare, and make a selection from multiple conflicting alternatives using disparate data sources and attributes, Gal et al., 1999, Nobrega et al., 2009. The applicability of MCDM is being extended to many different fields including GIS, which is capable of handling massive amounts of geospatial data. Analytical hierarchy process is a decision-making approach introduced by Soddy, 1994, based on pairwise comparisons among criteria and factors in different hierarchical levels. AHP is presented as an effective technique for combining heuristic inputs from stakeholders to achieve a consensus-based decision. The technique allows competing agency expert views as well as stakeholder opinions to be considered quantitatively in the decision-making approach, McFarlane et al., 2008. In keeping with the spirit of NEPA, AHP does not pre-select any specific alternative, it exposes all potential alternatives to the analysis and selection process.